Alô? É uma satisfação estar aqui apresentando o Kiung-Han. O Kiung-Han está vindo aí através de um projeto de colaboração, FACEP-MIT. Né? E o Kiung-Han, eu tive a oportunidade de conhecê-lo quando eu estava no meu pós-doutorado lá no MIT. Comecei meu pós-doutorado em 2006. Em 2007, Kiung-Han se juntou lá ao grupo. E Kiung-Han, ele teve toda a sua formação em física, né? E ele é um especialista em lasers como poucos, né? Ele, ao longo da sua carreira, ele se envolveu no desenvolvimento de lasers em fibra, né? Lasers em cristal, desenvolveu amplificadores para esses lasers, compressores, né? Toda essa tecnologia, principalmente laser de femtosegundo, que o Han é um especialista como poucos, tanto para fazer quanto para caracterizar esses lasers. E ao longo também da sua carreira, ele se envolveu em diversos experimentos utilizando os lasers que ele mesmo constrói. Experimentos de filamentação, geração de terahertz, como ele vai falar aqui para a gente, geração de altos harmônicos, mistura de onda, e, enfim, né? Aceleração de elétrons, né? Utilizando laser. Né? E, bom, Kiung-Han, essa é a primeira visita do Kiung-Han aqui ao grupo. Ele deve vir aqui outras vezes dentro dessa mesma colaboração. Ele vai ficar aqui até sábado. E aí, quem quiser, obviamente, conversar com ele, vai ter a oportunidade aí, durante o resto da semana, conversar com ele. Kiung-Han, muito obrigado.
Thank you for introduction. I already gave a talk yesterday, so I try to not overlap the topic from yesterday too much. But still, the first maybe 1/3 of the part might be very similar to what I talked yesterday, because I know that some of you didn't attend yesterday's talk. So today's talk is about the strong field mid-IR terahertz sources for soft X-ray high harmonic generation and electron acceleration. Okay, I'll just introduce our group again. So our group belongs to optics and quantum electronics group at MIT. So we used to have three main investigators, Professor Eric Ippen and James Fujimoto and Franz Kaltener. And I became a principal investigator 3 years ago. And then Eric retired, and then Jim also is working on the medical optics. So only our group is now actively working on the ultra-fast laser science. So main research theme is to develop novel laser sources covering entire terahertz all the way down to hard X-ray range. So this is our group. So there have been a lot of contributors to this talk, and including our group leader, Franz Kaltener. So he's now running another big group in Germany. He already have more than 40 people over there. So we are doing still the similar research. So we had former group members, including Edison, and also we have some collaboration with MIT Lincoln Lab, and also CFL in Hamburg, also with some other theory group in the US. This work has been funded by DARPA HRS program, and also DARPA Axis program, and also Air Force Research Office of Scientific Research, and also CFL DAGE Hamburg. So my visit here was funded by MIT Brazil Seed Fund, as Edison explained. So it was, I'm very glad to be here to have a chance to talk about our group's work. So this is the spectrum of the electromagnetic waves. So basically, using the ultra-fast nonlinear optics technique, in our case, we want to use a strong near-IR picosecond laser and ultra-broadband near-IR seed. We want to cover entire bandwidth from terahertz to all the way down to soft X-rays. So I'm going to mention the hard X-ray stuff also at the end, briefly. So in this research, we really used most of the available Chi2, Chi3 based nonlinear optical processes like optical rectification, difference frequency generation, optical parametric chopper amplification, and so on. So the first part of my talk is about the high harmonic generation. So as I mentioned yesterday, by accessing this ultra-fast high flux X-rays and strong field mid-dial and terahertz pulses, we can have a lot of applications in the time-resolved studies and the biological imaging and aerospace science and electron acceleration and LiDAR stuff. So in this talk, I'm going to talk about the aerospace science and electron acceleration. So yesterday, I briefly showed some data on the LiDAR and the filamentation. So then the first part of my talk is about the strong field physics in the mid-dial fields. So I'm introduce the strong field physics, and I'll show you our laser source, which I also showed yesterday, strong field mid-dial sources based on the OPSPA technology. And so I'll show some soft X-ray high-harmonic generation and some spectroscopy result. Then the second part of my talk, I'll talk about the terahertz-driven electron acceleration, which is maybe quite new in this field. So I'll introduce the laser-based compact accelerator research, and I'll show you some experimental effort in our group about the strong field terahertz source based on optical rectification, and I'll show you some recent result about the terahertz linear acceleration of electrons. And then summarize my talk, and I'll briefly show some our recent effort on the inverse Compton scattering project. Okay, I'll go to the first part of my talk. So yeah, this is also I showed yesterday. In the perturbative nonlinear optics within this kind of intensity, 10 to 9, 10 to 12 watt per square centimeter. So the nonlinear process is determined by the polarization in terms of the chi1 and in terms of the nonlinear polarization like chi2, chi3, and so on. So by using the ultra-fast, ultra-short pulse lasers and high-power lasers, you can easily access this chi2, chi2, chi4, even higher order nonlinearity very easily. That's the main theme why we are using the nonlinear ultra-fast lasers here. And then, yeah, you can see many nonlinear optical phenomena like second harmonic, third harmonic generation, self-phase modulation, and fourth harmonic generation, and so on, based on the chi2, chi3. And yeah, as I showed yesterday, the supercontinuum generation and laser filamentation are one of the extreme cases in the chi2, chi3 process. In this talk, I focus more about the strong field physics. So I'll start with just one photon ionization. As you know, in the visible laser light, visible light cannot ionize the atoms very well because the photon energy is not high enough. So in the 1 micron, so for example, 600 nanometer range, the photon energy is not high enough to excite the one atom. But if you go into the UV or EUV region, you can have some just simple absorption, and you can get the ionization directly from the ground state. But if you are working in the near IR range, you need a multiphoton ionization, right? So to get the ionization, so for example, if you have some n number of photons, you can have the same kind of ionization process. So when you have the same as the nonlinear optics, if you go into this high intensity regime, you can easily access this multiphoton ionization. If you have even higher energy, like in the strong field regime, which I'll describe here, the ponderomotive energy is given by, which is proportional to the laser intensity and the lambda square. Lambda is the wavelength of the driver. So ponderomotive energy is the average quiver energy of the electron in a cycle of electric field. So this basically the electron can get the kinetic energy defined by this energy. And Keldy's parameter is defined by square root 2 IP, where IP is the ionization potential divided by UP, this ponderomotive energy. Then if you have, for example, very strong electric field when the UP is strong enough, and then Keldy's parameter becomes smaller than 1. When you have Keldy's parameter of 1, we call this is the transition point between the multiphoton ionization I mentioned and then strong field regime. So what happens in the strong field regime is that you start, because of the electric field, you start distorting the atomic potential. So you don't need full IP to get the ionization. So if you have some IP, some excitation into here, and then you can directly ionize into the free space. So you don't need the full multiphoton ionization. So when you have Keldy's parameter close to 1, you have some kind of this kind of mixed state. You still need some multiphoton ionization, but you can see you can have a higher ionization rate because of this distortion. So if you go to this kind of regime, the high harmonic generation is one of the representative phenomena in the strong field physics. So what happens is that when you have the intensity of 10 to 13 or even 10 to 14 watt per square centimeter, your IP, your Keldy's parameters becomes very small, and you start observing the tunnel ionization into the free space in this direction because of the distortion. And then the electron get the kinetic energy in this strong field. Then the next cycle, and in the next half cycle, when you have a different opposite direction of the electric field, the electron start recombining into the parent ion. And then this process emits the light corresponding to the photon energy of ionization potential plus the kinetic energy given by this ponderomotive energy of the electric field. So this happens every half cycle of the driving field, and then that's why we are able to generate some coherent photons in the XUV range. This photon energy usually corresponds to EUV and soft X-ray range, and also, as I explained yesterday, this recombination happened within half cycle of the driving laser pulse, which is corresponding to about sub-femtosecond or arrowsecond duration. So this opens up the new field of arrowsecond science because we are generating arrowsecond XUV or soft X-ray pulses. So if you go even into the higher intensity, we can reach up to relativistic regime. For example, at 800 nanometer, if you go up to 2 times 10 to 18 watts per square centimeter, you start the Kiva velocity approaches the speed of light. That means you can accelerate the electrons up to almost speed of light. So we typically have 0.5 MeV of electron is the borderline for the relativistic regime. So in this regime, the B field here in the Lorentz force, usually when the velocity is small, this can be neglected. But when you have the V close to C and then B, the magnetic field becomes also important. So you can push the electron to the direction of the K vector. So the electron trajectory becomes quite complicated because of both E field and B field. So in the relativistic regime, you can see a lot of interesting phenomena. So now people are developing in Europe or in Asia and in the US, developing petawatt or even 10 petawatt laser to see this kind of effect. So I'm going to briefly mention, I go into this one again in the second part of the talk. So I'm going back to the high harmonic generation. This is a basic, typical structure of high harmonic generation. You have some multiple, this kind of harmonic up to typically 100th harmonics, and then all other harmonics because of the inversion symmetry of the gas. And then you have a sharp cutoff here, where the cutoff is determined by the ionization potential plus 3 times this UP, this ponderomotive energy. As you see here, the UP is proportional to the lambda square. So if you want to scale the cutoff, you can play with wavelength. But when you play with the intensity, you are generating too many plasmas, and then it's hard to get the phase matching between the driving IR pulse and the generated XUV. So it is much more advantageous to use a longer wavelength driver to extend the cutoff. So that's what we came up with, actually. Okay. This is Edison's work when he was at MIT. So if you want to generate, for example, 500 eV or higher, you have to use 2 micron driver here rather than the typical tight sapphire laser wavelength at 800 nanometer here. So when you work with tight sapphire lasers, it's hard to go much more than 150 eV. So the main takeaway is that if you want to reach more than 300 eV, you have to use a wavelength longer than 1.5 micron here, and depending on the gas species we use. Also, we have to note that unfortunately, because of the longer wavelength driver, the electron the excursion path into the free space when it recombines into the parent atom, it's much longer. That means the probability of recombination into the parent atom is much smaller. This is 3-dimensional, and there's some quantum diffusion. So there are some other factors included. So that gives us a little bit unfavorable efficiency scaling. For example, if you use twice longer driver wavelength, and then the efficiency dropped almost 50 times, which is a little bit too bad. But to overcome this problem in the single atom response, you need to accumulate more atoms involved to generate more photons. So that means that you need a good phase matching. So it turned out that we need a very high pressure gas to reach the phase matching in the mid-IR wavelength, which I will show you later. So for example, a few years ago in Gilla group, in collaboration with Vienna Vienna Technical University in Baltuska's group, they demonstrated the cutoff extension up to 1.6 kV here. They used the 4 micron, 3.9 micron OPSPA system operating at 20 Hertz. Then they showed really good cutoff extension. So in that case, they had to use up to 35 ATM in helium, which is really high pressure gas cell. But as I will show in the next slide, the typical gas pressure in the interaction region is only 200 millibar. So compared to this number, this is quite challenging. So that's what people found so far. And then this is the highest cutoff ever generated from the high harmonic generation. But we are more interested in the water window range here. So they already showed some water window extension using the 2 micron system they had pumped by the tight sapphire laser at 10 Hertz, which was demonstrated about also 5 years ago. They showed the cutoff extension up to 500 eV here. But if you look at this part, you have carbon edge, and nitrogen edge, and oxygen edge. Especially the carbon edge to oxygen edge is called the water window soft X-ray window, because of the good, the biological species have both carbon and oxygen, and if you have the soft X-rays in this range, you can, in principle, get the biological imaging of the living cells. So this kind of experiment has been demonstrated in the synchrotron facilities with very high photon flux they have. They can generate up to 10 to 12 photons per second over 0.1% bandwidth, for example, from APS in Berkeley. So typical requirement for this kind of experiment is a 10 to 10 photons per second over this kind of small solid angle and narrow bandwidth. So our question was, can a tabletop high harmonic source reach a flux enough for biological imaging like this in the water window soft X-ray region? So we want to answer this kind of question. So another application of this kind of high harmonic generation process is the high harmonic spectroscopy. So because we have an extended cutoff, so using a mid-IR driver, you can extract more information from the high harmonic spectrum. So that that makes us to extract the recombination cross-section from our high harmonic generation measurement. So when the electron is ionized and recombined, the recombination cross-section actually determines the structure of the high harmonic generation. This is represented by the transition dipole here, then also which can be translated into the photo recombination cross-section. So that means that if we know the high harmonic spectrum here, and if we know the wave packet of electron trajectory, then we can extract the photo recombination cross-section, which means we can have more information about atomic or molecular structure or orbital structure. So the extended cutoff helps a lot to get more information, which I'll show you in one of the experimental data. Okay, and I'll move on to the strong field mid-IR OPCPA system we developed, also which I presented yesterday. So this is the main idea of the OPCPA system. So this is a combination between the optical parametric amplifier and also chop pulse amplifier, CPA. So we stretch the seed and get the amplification from kite to process based on the OPA. And then we get the high energy pulse and we compress the pulse again without any medium. So the main advantages compared to the tight sapphire based CPA system when you use this kind of OPCPA system is that we can select various wavelengths as needed from UV to all the way to mid-IR. So there's no gain narrowing involved here. So you can amplify ultra broadband pulses directly without the gain narrowing. So also average power and energies are scalable if we have a good picosecond pump lasers. So these are the main advantages of using the OPCPA technology. So we pursued this technology from maybe back in 2007 when I started my job at MIT. Then we tried several steps to make it work. So also it has to be noted that we need multimillion mid-IR driver to get the phase matched high harmonic generation in the soft X-ray water window range. So our target is to generate kilohertz rep rate to keep the high flux and also generate the multimillion mid-IR femtosecond laser pulse. That's the main goal of our this mid-IR laser technology. So to realize this process, this setup, we came up with the ytterbium doped pump laser technology. So in this amplifier, we chose ytterbium YAG amplifier, cryo-cooled here, with a high gain cross-section. And then we chose ytterbium KYW amplifier to provide more broader bandwidth from the beginning. If you cool down the ytterbium YAG crystal, your cross-section enhancement, laser cross-section is enhancement dramatically, but your gain bandwidth is reduced. So to compensate this one, we start with the KYW amplifier, and then we final amplifier were composed of this cryo-cooled ytterbium YAG crystals amplifiers. Also, this technology is compatible with the ytterbium doped 5 amplifiers, which is very convenient for high average power applications. So this is the latest status of a pump laser. So we start with the ultra broadband tight sapphire oscillator. So we pick up the 1 micron part here. So out of the ytterbium doped 5 amplifiers, we are going through the top volume Bragg grading stretcher. Then we stretch the pulse up to almost 1 nanosecond, and then the pulses are going through 3 solid-state amplifiers. The first one is the ytterbium KYW regen amplifier. The 2 multipass amplifiers are based on the cryo-cooled ytterbium EAG amplifiers. And then we compress the pulse down to 6 picosecond. So we obtained up to 70 millijoules here. So, okay, this is the setup we have now in the lab. So this is the seed laser is coming through this regen amplifier from down here, and then going through the 3 stages amplifiers, and then we are generating, for safety margin, we are usually generating 50 to 60 millijoules here, and then we bring the pulse into the other side where OPCPA is located. And then this is the system I just showed. That this is the main part for the power scaling of our OPCPA system. To realize the mid-IR femtosecond mid-IR multimillijoule driver, we start with the same Tie-Sapphire oscillator spectrum. So we have the difference frequency generation between the intra-pulse. From same pulse, we can do the difference frequency generation between 650 to 950 nanometer. We can generate ultra broadband 2.1 micron source. And then we are going through 3 amplifiers. So the first 2 stages are pumped by a neodymium amplifier, generating 1 millijoule here. And then we have 25 microjoule here. And then the last amplifier is pumped by a 40 millijoule ytterbium EAG amplifier we developed. And then we can go up to, now we are generating more than 3 millijoule here. So this is a multi-millijoule to micron system operating at the kilohertz repetition rate for the first time. And this is our pulse duration I showed you yesterday. So we typically have 35 femtosecond with 400 nanometer bandwidth and good beam profile. M-square value is typically 1.5. So we have a good focusing quality. So we believe that this provides the platform for the next generation strong field laser source, so covering the mid-IR and the other wavelengths too. So, and then I'll show you some data about the soft X-ray high harmonic generation and spectroscopy. So we bring our pulse into the high harmonic chamber in vacuum. So because we are dealing with the soft X-rays or XUV, they are all absorbed in the air. So we need a vacuum system. So we focus the beam into the gas target, or depending on what kind of target it is, we use gas puff or gas cell or hollow core fiber. And then we simply use X-ray filters to block the IR, and then we let the XUV go through the toroidal mirror and XUV spectrometer to measure the XUV spectrum. This is the chamber and XUV spectrometer developed by, actually fabricated by Edison. And then these are the data we got about 4 years ago. So we started with xenon gas, which has the lowest ionization potential among the noble gases. So we extended the cutoff up to 85 eV. So I have to mention that if you use an 800 nanometer Tie-Sapphire laser, the cutoff is only here, the 30 eV or even 25 eV. So you can see the dramatic cutoff extension. The efficiency was about 10 to minus 9 per harmonic from the driver, which is pretty low, but still not so bad. So if you use a krypton, that's 50 millibar, a little bit higher intensity because it has a little bit higher ionization potential. So you can extend the cutoff up to 120 eV with the similar efficiency at here. And if you move on to the argon, which has even higher ionization potential with higher pressure, we can extend the cutoff up to 160 eV. And the efficiency is also was in the same range. And also I can mention again that using the Tie-Sapphire laser, you can go up to only 50 eV or 60 eV. So you may be able to see the Cooper minimum here at 53 eV using the THz amplifier system. But if you use this kind of mid-IR driver, it was much easier to see this kind of Cooper minimum here. So I show you one example of the high harmonic spectroscopy. If you look at this data from Krypton, you can see some deep minimum here, right? Because when you have the THZ laser, the cutoff is already also limited at around 60 to 80 eV. So it is hard to see this minimum visually. But when you have the 2-micron driver, you can see this minimum structure clearly. So we look into more details about why we see this kind of minimum structure. And then it is related to the photo recombination cross-section I mentioned in the previous slide. For example, this is the experimental data. So let's say we don't know this experimental data. Then we can simulate the electron wave packet from our experimental condition. This is the high harmonic generation without considering the photo recombination cross-section, actually. And then we can calculate the photo recombination cross-section, which is given by the 4p orbital from Krypton, which can be found from some literature. I didn't show you here. If you combine this red curve and this high harmonic curve together, you can come up with this kind of high harmonic structure, which is very close to what we measured actually from Krypton. So we can see the good agreement between our simulation and the experimental data. So if you go the other way around, for example, if you do not know about this red curve, photo recombination cross-section, let's say by combining this simulation data and then by using this experimental data, we can also extract this red curve. That's what I tried. So the dotted line here is the experimental data we extracted from our experimental high harmonic generation curve. Then we came up with this kind of curve, which has a good agreement with the 4p orbital, which is the valence shell of the Krypton. So I also take a look at the 4s shell, which is the next subshell of the Krypton. So it seems like there's some influence from this 4s shell if you compare with this data, but it was not clear enough. But this is a good example of how we can access to the orbital structure using the high harmonic generation. So this kind of technique is called the high harmonic spectroscopy. So if you use the same technique to the molecules, you can also look at the molecular orbitals, which is more complicated, but which is more interesting. So I'll move on to the soft X-ray water window high harmonic generation. To handle the higher pressure, in the previous data, we used a gas jet, but in that case, the actual pressure in the interaction region is only up to 200 millibar. So it was better to use a gas cell where we can directly go up to several bars at the interaction region using neon gas or helium gas. So we also developed a hollow core fiber system here in a gas cell. Actually, this was made by Jonathan Sequeira in UFPE, Sao Paulo. So we tried on both cases. So this is the data from the gas cell. So we use argon gas and then extend the cutoff a little bit more up to 190 eV with a photon flux of 2 times 10 to 8 photons per second at 1% bandwidth here. And also we tried nitrogen, which has very similar ionization potential as argon. So we were able to get the same cutoff as expected. So, and then we move on to the neon and helium. Before showing that this is a simulation data about this spectrum. So we are able to reproduce the simulation, the experimental data from our simulation using our 3-dimensional propagation code and this, including the photo recombination cross-section calculation here. And then the temporal structure looks like this. So the red curve is the driving IR laser. So we are generating harmonics in the front of the peak of the IR laser pulse. These are the attosecond soft X-ray harmonics. Each pulse has about 200 attosecond pulse duration. So this can be actually used for interesting subshell excitation experiment. So this can be also measured directly using so-called flow-craft techniques or other attosecond lighthouse techniques and so on. So, and then we move on to neon gas to demonstrate the water window soft X-ray generation. And then actually we got quite good signal from the X-ray photodiode with the carbon and titanium filter, which blocked all the light below 200 eV. And then we got some 10 to 6 photon per second over 1% bandwidth from this measurement we did actually last year. So this is actually the simulation spectrum. This is the titanium filter curve. And it turned out that our XUV spectrometer has been contaminated by other things, and then we are not able to measure actual spectrum. It was very difficult to measure the spectrum above 200 eV. So we show the simulation spectrum like this. Then our experimental measurement from the photodiode shows that we have the photon flux of 10 to 6 at this 330 eV here. But we confirm that we are generating the water in the soft X-rays. And then since last year, we cleaned up the XUV spectrometer and we repaired everything on the line. And then finally, in this July, we reproduced the experiment using the helical fiber system, which is lasers coming into here, and then we have a fiber here. We are generating some filament here, and harmonics are coming out from here. We finally measured the water in the soft X-rays as shown by this curve from the titanium filter, and this is the carbon edge. Well measured here. So finally, we were able to generate the soft X-ray water window generation at kilohertz repetition rate from our 2-micron system. So photon flux was a little bit higher than we measured from previous slide, but still in the order of 10 to 6 photon per second over 1% bandwidth. But it has to be noted that we covered up to nitrogen edge already. The oxygen edge is here, but we mostly cover the water window soft X-rays. Some groups also claim that they generated the water window soft X-rays, but they reached up only here, just 300 eV carbon edge actually. So these soft X-rays are really useful for actual applications in terms of the carbon edge or nitrogen edge spectroscopy, absorption spectroscopy, as well as some biological imaging. Okay, this is a summary of the part 1. And so we demonstrated the novel mid-IR OPCA technology and high-flux tabletop soft X-ray generation. Okay, and then I move on to the second part of my talk. It is about the tethers-driven acceleration. So I'll briefly introduce the compact accelerator-based X-ray sources. So this is actually LCLS in SLAC in Stanford, which is the first X-ray FEL laser source demonstrated around the world. So actually they are generating millijoule level hard X-rays with 100 femtosecond duration, which is quite really new source. So you can do a lot of interesting X-ray science out of this kind of source. But this is based on the linear accelerator, actually spanning more than 3 kilometers, 50 GeV electron beam here. So it is kind of one village here. So also the cost of this kind of machine is multi-million dollars. So you cannot even think about constructing this kind of machine in the university. So many people have dreamed about the tabletop coherent X-ray source. So one of the option is the high harmonic generation I showed before, but it's hard to reach up to hard X-rays. So the other way of going into the hard X-rays tabletop source is the inverse Compton scattering, which is the basically same as the Compton scattering or Thomson scattering. Just you have the high energy electron beam and your IR beam are colliding each other, and then you can generate the hard X-rays. So this can be realized on the tabletop. So this is one of the goals we pursued over the last 5 years. And then in parallel, there are a lot of other techniques generating some for the electron acceleration. So in this process, you also need some high energy electrons. So electron acceleration is compact electron acceleration is the prerequisite for this kind of research. So people work on the laser plasma wave field acceleration. So people demonstrated up to almost GeV energy directly from the laser produced plasmas. Also, when I was in Korea, we also demonstrated up to 300 MeV or even GeV from this kind of experiment. So there have been 3 Nature papers published at the same time in the same issue in 2004 about this kind of result. And then very recently in SLAC, they used the dielectric structure like this kind of, they mimic the crystalline in an optical version. So they excited this kind of dielectric structure such that electron can be accelerated at each stage. So they demonstrated up to some tens of keV acceleration starting from 40 MeV electrons. So they have a little bit of acceleration into this direction. But it was published in Nature 2 years ago. So in our group, these are all laser-based accelerator. We thought about the terahertz-driven acceleration. So terahertz is in the middle of RF and optical domain. So in terms of the wavelength, it is in order of 100 micron to a millimeter. The bunch charge, because it can be tight, it doesn't need to be tightly focused. We can handle the bunch charge up to 100 picocoulomb compared to the optical domain, which should be focused very tightly, and the volume cannot be so high, so the bunch cannot go much higher than 10 femtocoulomb. In terms of the acceleration gradient from the electric field, so terahertz is still high enough compared to the RF accelerator. That means that you can make it very compact. It cannot be higher than the optical field, but you can make everything within some centimeter order, the accelerator. So that's why we chose the terahertz pulse for acceleration. But main issue is that the high energy terahertz were not available. So, but nowadays people are working very hard to generate really millijoule level terahertz. So it can be more realistic, not at the moment. So one of the simulations we did to explore this kind of possibility was the terahertz acceleration inside the waveguide. So we use a radially polarized terahertz, and then we launch the terahertz into the waveguide, and we are generating TEM10 mode, which means that your E field is in the same direction as the propagation in this direction. So electron can be accelerated directly from the axial components of the terahertz. So, but in this simulation, we used up to 10 millijoule terahertz, so which was not experimentally available. But this shows a good scaling capability. Like you can, if you have an input electron energy of 10 MeV, you can go up to accelerate electrons up to 35 MeV, which sounds quite interesting. So what we try with also in the previous DARPA program, we wanted to use this kind of terahertz accelerator in the, this is an inverse compton scattering source, but this is the terahertz accelerator we wanted to implement, so which can be very compact. So this is the inverse compton scattering stage where the IR pulse is colliding with the electron accelerated here. So we want to generate a coherent X-rays out of this in this direction. And actually, to generate a strong terahertz field, we need a good technique to do that. So we relied on the optical rectification in the lithium niobate crystal in cryo-cooled. So so-called pulse front tilting technology technique using a grading, so we can get a phase matching between the terahertz and IR pump and the generated terahertz pulse, which has a really big difference in the refractive index. So we tilted the wavefront and then we get some phase matching inside the prism. And then terahertz is generating in a tilted way, not in the same direction as the IR. By using this technique, also by cryo-cooling the crystal of lithium niobate, you can minimize any absorption of the terahertz itself into the crystal. So we are able to get more than 1% conversion efficiency from the IR, which was the record high number at the time. So we were able to reproduce this one. And this is the generated terahertz. And then this is a spectrum. This is the E field and the spectrum. The center wavelength is, center frequency is about half terahertz. And then bandwidth is about 0.5 terahertz. The terahertz beam profile is pretty good with the diffraction limited quality. And then, okay, I didn't, I already mentioned, but this was obtained in the room temperature, and then we cooled down the crystal, and then we were able to get the enhancement of a factor of 3 because of the absorption is minimized. So we believe we generated more than 3% conversion efficiency, which was reported in this paper. So in principle, if we have, this was pumped by 1.5 millijoule IR pulse, 500 femtosecond and 600 femtosecond pulse. But if you have some 100 millijoule pump energy, we can reach almost up to some millijoule level terahertz energy. So this is quite interesting, promising technique for the future. This is the IR spectrum, which has some extension to the longer wavelength because of the cascading effect. So you generate the terahertz here, and then wavelength is shifted to next part, and then generate the terahertz here, and then shifted again, shifted by about 13 times, and each time we are generating terahertz. So, and that's why we were able to get high efficiency terahertz, almost 10%.
That center frequency corresponds to which wavelength?
This one?
No, the 0.45 terahertz. Terahertz frequency corresponds to which wavelength?
0.5 terahertz.
Yeah.
So 1 terahertz is, it should be 300 micron, right? So we are talking about 500 micron in the wavelength. So diffraction limited beam size is about millimeter, 1 millimeter.
And could you comment what typically, commercially, what kind of source for terahertz at that wavelength do you have available?
A good question. If you rely on this optical rectification process, so you typically have the frequency below 2 terahertz, 0 to 2 terahertz range. But if you are relying on, for example, DFG, difference frequency generation, you can generate up to 100 terahertz. From 10 terahertz to 100 terahertz frequency can be generated. But if you use, for example, other technique like photo inductive process, you are generating some CW, some tens of terahertz range. So there are a lot of different technology, but we are relying on this nonlinear optical technology like rectification or DFG.
Those other technologies, they are capable to produce, for instance, those cycle therapy?
I don't think so. Yeah, in terms of the single cycle terahertz generation, the optical rectification is the best method. So you can clearly see the single terahertz source here. But I have to say that for this kind of acceleration process, multi-cycle is better because monochromatic and some periodic acceleration can give you a higher acceleration gradient at the end. So now we are working on a little bit multi-cycle terahertz generation.
In terms of peak
Peak
power?
power, I don't know the number, but I can talk about the gradient in terms of volt per meter, which is typically we can reach up to some almost MeV, megavolt per meter. So within centimeter, we can have some tens of keV acceleration. But if you have millijoule level terahertz, you can reach up to some 100 MeV per meter, which means you can directly get MeV electrons from centimeter of waveguide. Okay, I'll show you this is the last part. So one of the applications of the terahertz acceleration is shown here. So we fabricated the terahertz waveguide, which has a metallic outer diameter, and then dielectric is loaded into the metallic cylinder here. And then we changed the polarization of the terahertz using the segmented wave plate. So we have a radially polarized terahertz here. If you have focusing into the waveguide, the axial component of the polarization inside the waveguide, radial components are all cancelled out. Only the axial components survive. So we can launch the TM10 mode in this case, as I mentioned. And electron is going this way. Actually, there's some other stuff, but so electrons are generated from a DC electron gun. So they meet inside the waveguide. That's what we did. And then this is the input terahertz pulse. This is actually the terahertz pulse after the waveguide. So because of the waveguide dispersion, we have some spectral filtering inside the waveguide, and then we have multi-cycle terahertz pulses here with narrow bandwidth. And then this is the terahertz pulse with a good beam profile. And this is a result. We input electron beam here. This was generated from DC electron gun, so which provide about 50 keV electrons with some 100 femtosecond picosecond duration inside the waveguide. So we use the UV to generate electron and then accelerate it using DC field like 40 to 50 kilovolt. And then we have the beam profile, electron beam profiles like here. So operating at kilohertz repetition rate. Okay, now we have the overlap of the terahertz and electron beam inside the waveguide. So when there is no terahertz, you have the electron beams like this. Actually, the red curve is the from the simulation. And then, okay, this is when we have the temporal overlap with the terahertz and spatial overlap with the terahertz inside the waveguide. So when you have the terahertz, you see the electron is kind of dispersed. So the one direction is going to accelerate it, and the other one is decelerated. Now the electron bunch length is order of picosecond duration, which means which has a little bit longer than the actual terahertz pulse. So you cannot accelerate the entire bunch of the electron to one direction or decelerate it to the other direction. So there's a mixture between the acceleration and deceleration inside the electron beam. So, but it clearly shows the acceleration of by the terahertz. So depending on the input voltage of the electron beam, so we can see some dependence of the terahertz. So in the case of 60 keV electron beam, we obtain the highest gain from the terahertz E field, so which is about 7 keV electron. So this is basically the first demonstration of the electron acceleration by the terahertz field. So if you now in this experiment we use only 9 microjoule terahertz energy, but if you, for example, use millijoule terahertz energy, you can directly go up to some 100 keV or even MeV electrons, which is in relativistic regime. If you go to the relativistic regime, there is no slip between the electron and the light, because the speed of both electrons and light are close to each other, which makes even more easier to accelerate the electron, because there is no slip in the phase between the electron and the terahertz field. So, but this demonstration is quite valuable because this is still in the non-relativistic regime, which is more difficult. So this will be, will appear the Nature Communication maybe next month, I guess. So this is a summary of part 2. So we demonstrated the record high optical to terahertz conversion from the optical rectification process. Then we showed the 7 keV electron acceleration from the terahertz field, which is the first proof of principle experiment, which can be scaled up to some MeV range with a gradient of almost GeV per meter if you have 10 millijoule terahertz pulse. So we also demonstrated terahertz electron guns, but because of the limited time, I do not show in this presentation. I just spend 1 more minute. So this is actually our previous DARPA project at MIT actually was canceled because of some economic problem in the US. So now we found another funding source in the Arizona State University. So now we are developing actually inverse Compton scattering source, which is the schematic diagram. The same, we have a linear accelerator, either or terahertz driven accelerator or just conventional RF accelerator. And then we have the laser here. They are colliding inside the vacuum here. So we are generating X-rays, hard X-rays. So this is the lasers for this kind of technology. So we need the photocathode laser to generate the photoelectrons, which can combine, collide with the inverse Compton scattering laser here. So we are actually constructing this facility in Arizona State University, which will be completed in next 2 years. This is one of my new project, so I'm just introducing. So, for example, in the university scale, this kind of hard X-ray source or the soft X-ray source based on the high-harmonic generation can be really developed with a still budget is some multi-million dollar, but compared to the real accelerator facilities, this is quite manageable. So if you are interested in this kind of research, you can start developing this kind of compact tabletop hard X-ray source as well, maybe here in Brazil or somewhere. Okay, thank you for your attention.